Hello, Mr. Kitchen, Global Skill Richmondville High School Physics. This is the first in a series of videos where we're going to take you through the review guide. Most of you have probably done this in class, but if you haven't, now's a good time for you to get caught up. So we begin our review outline with mechanics, specifically kinematics. And the first distinction we're trying to make is the difference between distance, which is a scalar, and displacement, which is a vector. Displacement tells us how far and in what direction, and that is always from the starting point. So if you go around in a circle, your distance is pi d, but your displacement is 0. Similarly, we have speed and velocity. Speed is our scalar. It tells us how fast you're going. Vector, how fast and in what direction. Vectors always have two parts, a magnitude and a direction. Now we come to the graphs of distance and velocity time. So what you really need to know is that the slope of a distance time graph is velocity. And so over here in the left-hand margin, we'll just sketch a little distance time graph. This is time in seconds. Distance, of course, is in meters. Let's say we have a linear relationship here. The slope of this graph represents velocity. So this would be the graph of an object traveling at constant speed. If something were accelerating, its velocity would be changing, and we would have a curve instead of a straight line. The slope of a velocity time graph is acceleration. And once again, if we sketch an acceleration time graph, a velocity time graph, and let's say I do the velocity time graph for an object that's been thrown up in the air and then comes back down. That graph is also linear because we have a constant acceleration. This acceleration would be equal to g, in this case, negative 9.81 meters per second per second. Over here in the top we have positive velocities. Here we have negative velocities, and right here where we cross the origin, that's where the velocity is 0, and that's where the object at the top of its flight. And finally, in terms of graphs, we have the area under a velocity time graph, and that is displacement. So in math, when you calculate area, you're always calculating area in square meters, but we've got different set of units here. So we've got velocity and time. Let me use the same kind of graph that I have above, but if I want to figure out how high the object goes, I could take a look at this area, say here, under the graph. Now this is the upward part of motion, and if I found the area of that triangle, the area would be the displacement in meters. It would tell you how high you went. If I did the area down here and this part below the x-axis or the time axis, we could have a negative area, and that just means negative displacement. That means the object is coming back down or coming closer to the point where it was released. All right, just moving on a little bit. Acceleration is a vector, and that represents a change in speed or direction. The units are meters per second, or you can write it as meters per second squared. A negative acceleration doesn't mean the object is slowing down. The object could be speeding up in the negative direction. So if acceleration and velocity are in opposite directions, then the object is slowing down. So you can have a positive velocity and a negative acceleration, or a negative acceleration and a positive velocity, and the object is slowing down. Problem solving with accelerated motion, we're going to start with our mnemonic device. Very important. Teachers, always vote for Democrats, or any other D word that you like. We've got our equations of accelerated motion here. These are 3, 4, 5 in mechanics. And when something's in free fall in a vacuum, all objects fall with the same acceleration, that is negative 9.81 meters per second squared. If it falls freely from rest, then v initial is 0, and your distance can be 1/2 gt squared. So I'll leave this up to you as a little exercise that you can show me. How far does an object fall in 1 second and in 3 seconds? But I'll give you a hint. Neither one of those is negative 9.81. Okay, so we're going to continue on. And our next little piece here is statics, which are when we have objects at rest. If we have concurrent forces, that means that we have 2 or more forces acting on the same object. The resultant is the vector sum of the concurrent forces, and most of the time we use a parallelogram method to add the forces. When we do this, we put the vectors tail to tail, and we draw the resultant along a diagonal. Make sure you include an arrowhead with your resultant, and this is a quick sketch of how we might do this. Let's say I have 2 vectors like this, and I've already put the vectors, I've drawn them tail to tail, and what we do using our ruler protractor ideally is we'd construct a parallelogram, something like this, just making 2 parallel sides here, and then our resultant is the diagonal. And don't forget to put on the arrowhead, the diagonal is always from where you started to where you ended up. So this is our resultant vector right here. If we can resolve vectors into components, and this tells you how much of the vector acts in each direction. When I say each direction, we normally mean the x and y directions. If you're doing the graphical method, what you do is you just start out by drawing the vector. So let's say I draw a vector like this. All we're going to do is draw in some guidelines. We're essentially going to put some light lines around this vector and make a rectangle. And then we can darken in a couple of the vectors here. This represents the x component, and this one over here represents my y component. So here's my vector in the y, and here's my vector in the x, where this was my original vector over here. So we draw components to form a parallelogram, but in this case it's actually going to be a rectangle. A rectangle is a parallelogram. Don't forget the arrowheads when you draw these component vectors. And we've already done our example. If we're going to use the analytical method, which we often do, it's faster and a little bit more accurate. We use the cosine for the x component. We use the sine for the y component. And we measure theta with respect to the x-axis. So that's the counterclockwise convention that we've talked about a little bit earlier in class. I'm not going to solve these components to the left here. But I will mention, if we have this vector over here, this is my angle theta, so I would take the vector times the cosine or the sine of that angle. And it's always measured from 0 degrees over to the vector. When we talk about equilibrium, that means the sum of the forces is equal to 0, or F net is equal to 0, and in that case we have no acceleration. The study of dynamics is all about how forces are acting on objects and affect its motion. And so we start with Newton 2, which is the most important law in all of Newtonian physics. And Newton 2 basically says acceleration is net force over mass, so it says net force causes accelerations. Once again, is Newton 2. It's a one-body law. That just means it has one mass in it. A Newton is defined as a kilogram meter per second squared. And if we draw a graph of force versus acceleration, this will be our force in newtons. And I should say force versus acceleration. This will be in meters per second squared. If we look at the slope of this graph, it would have units of newtons divided by meters per second squared. That gives us units of kilograms. and that implies that the slope of this graph represents mass. You can always figure out what the slope of the graph represents by taking a look at the units for the slope of the graph. And then we have a couple more Newton laws. Newton 1 is called the law of inertia. And inertia is the resistance of an object to a change in motion. It's directly proportional to mass, and although inertia doesn't have units, mass does, and the SI unit of mass is the kilogram. And we end up with Newton 3, which basically says forces always come in pairs. Each force is equal and opposite. Now, if these forces act on the same object, they would cancel out. So they never do. Each force acts on a different object. All right? So that's a quick rundown of some topics in mechanics, and that's the end of video 1.